Hello everyone. I'd like to thank you all for joining me for this webinar. My name is Philip Taylor. I'm Hydro International's product specialist for the stormwater products in our American operation. I've been with Hydro International for about 12 years now. I started my career in stormwater and erosion control with a water and soil district in New Zealand. I've worked in the UK and in the US, and for the last 12 years I've worked in stormwater quality with Hydro International. Now throughout those years I've learned a lot about stormwater, and what I find is that we get basic questions keep coming back all the time as we get new people in the industry. So this is a kind of an industry where going back to basics every few months is useful. It helps people understand where we've come from, what we're trying to do, and what tools we have to try and achieve better water quality, and why we've still got a long way to go. So having said that, I'll move forward into this webinar. We have about 200, a little over 200 people online at the moment. So a good turnout. We had something like 350 people register. From all over the country and Canada as well. So for the people in Canada listening in, I apologize, this isn't in metric. I'm going to be using US units in this presentation. If I can just get it to advance, that would be helpful. Okay, so at the end of the webinar, there is an exit survey. These surveys are very useful for us to help develop and improve on future webinars, so we really appreciate people taking time to fill out these webinars, fill out these exit surveys. Tomorrow we put a draw together, and everyone that fills out the survey goes into a draw for a $50 Amazon gift card. PDHs will also be issued, and they should go out tomorrow. If you don't see a PDH in 2 or 3 days, either check your junk mail. If it's not in there, just email our Hydro International, Bridget, or myself, and we'll chase that up. As I said, we had over 350 people register. We've got roughly 250 people online, so that's a really good turnout, and we really do appreciate that. The presentation is being recorded, and it will be available on Hydro's YouTube channel. And also, I've attached for your download a PDF copy of this presentation. I often get asked for copies of my presentations, so there is a PDF of that, and a brochure that covers all the products that we will use in this presentation to demonstrate some of the questions and answers that I'm going to cover. So an overview of today's presentation, which should take around 35-45 minutes, something in that range. A little bit about Hydro. We always like to introduce the company. I'm going to look at a bit of the history of regulation and the history behind regulation. I did a webinar on this a few weeks ago, and it is kind of fascinating where we've come from, so I'll just do a brief recap of that. And the basics of what we're trying to treat. You know, we're trying to treat sediment, remove pollution from rain and runoff, so we're going to look at that. And then we're going to look at some of the products and general tools that we have to actually do that. And then I'm going to follow up with a little bit of closing on flow control devices and treatment trains. So about Hydro International, it's a company that's been around since the sort of the mid-1960s, really. It first started to get developed with the invention of the vortex flow control device. That led to the development of vortex separators and the formation of the company. It's a UK-based company. We do work in over 33 countries. We have office locations in the UK, where the company is headquartered, 2 office locations in the US, one on the East Coast and one on the West Coast. Our East Coast office does all the stormwater work. The West Coast office tends to specialize in our wastewater and wet weather flow division. And we have people around the world that handle different markets. We work in the stormwater industry, wastewater, and combined sewer industry. So we have similar products across the industry. They do similar sort of things. They target pollution, sediment, and grit, and that sort of thing. You can't do this without having access to good research facilities, and we're very fortunate as a company. We have 2 world-class labs, one in the US, in Portland, Maine, and one in Cleveland, the UK. These labs allow us to do a lot of testing, a lot of research, and really back up our understanding of the industry. So these labs are our backbone to our business. They're working all the time on testing, development, and research. And in addition to that, we have a great deal of expertise within computational fluid dynamics, and this allows us to prototype and carry out analysis of equipment using computational fluid dynamics, which is a really useful tool when you're studying technology and you have an idea and you want to just get some idea of how it might work. So that's another tool that we have. That's our 3rd lab. We can't do all this without partners. We go to third-party research facilities and universities to help validate and benchmark what we do, to test what we do. We don't just say, take it from us, you know, everything we do is correct. We use third parties to basically fact check ourselves, to sanity check, make sure things are right, and also to help develop technologies. We often find that our technologies are coming out of these research partners, and they're looking for partnerships to commercialize new ideas. And this is an industry that spends a huge amount of time going into getting approvals, pre-approvals, and getting approvals to sell or to promote the products. It is one of our biggest cost centers, is going out and getting approvals. Perhaps one of the most researched part of our industry in the stormwater industry is the proprietary treatment devices. It's a hugely onerous part of our business, but without them, we can't really do much. So we go out there and chase these approvals religiously. So where have we come from? Well, we've come a long way, and what's driven this? You know, really through the middle of the century, the 19th century, you know, 1950s, 1960s, a lot took place. For instance, World War I, World War II particularly drove industrialization, and the manufacturing sector really ramped up through the mid-century period. But you know, as part of that development, waste was really just considered something to be just disposed of into waterways often. It was kind of amazing that they just viewed waterways as a natural sewer, basically to drop in pollutants and whatever waste you don't want, we'll just throw it in the water. Let's see if I can pronounce this. The Cuyahoga River in Ohio caught fire 13 times, dating back to 1868. This blaze pictured here took place in 1952 and was actually one of the drivers of modern regulation. People sort of got sick of water catching fire. Now, early regulation, it's kind of interesting, goes back to the late 1800s. The very first regulation I could find in the US was the Refuse Act of 1899 that referred to the dumping of refuse into navigable waters. You could do it, well, you couldn't do it except by permit, but the permit was written around that you could do it, you couldn't impede navigation. There was nothing about pollution in there. It was purely about, sure, you can dump that stuff in there, just don't stop the traffic from flowing down the river. So as long as you didn't impede navigation, you're pretty much allowed to dump whatever you liked into the river. It's kind of crazy when you think about it now, but I guess in those times it was a different time, and they looked at the rivers as just a way of being used for progress. So somewhere around 1948, the Federal Water Pollution Control Act was written. And this was the first major US law to address water pollution. Its purpose was to formulated around restoring and maintaining the chemical, physical, and biological integrity of the waters of the United States. It was to support and aid technical research. Unfortunately, the Act itself didn't achieve a lot because it wasn't really written around prohibiting pollution. It gave only limited authority to the federal government and really pushed a lot of it onto the states and really created a very cumbersome and unworkable mechanism to enforce. So it basically went nowhere. We also had the National Environmental Pollution Act, which came in 1970. Now, this was the first of the laws written around pollution. And it gave authority and powers to branches of government to deal with pollution. And it created the Council of Environmental Quality, and it led to the formation of the Environmental Protection Agency. So it did a lot of good. This act, I believe, is modeled around the world. So what drove the North American Pollution Act? During the sort of, as I said, in the midst part of I'm sorry, my screen keeps going black. I'm not sure what's going on. Hopefully you're seeing the screen here. I think you are. What drove the North American, Pollution Control Act? Here we have Environmental Pollution Control Act. There were a number of things going on in the mid part of the 19th century. One, as we were seeing the river catching on fire. There was also huge interstate build out. Post World War II, the interstate freeway construction took off. That was disastrous to many city neighborhoods. It cut people's lives in halves, it cut the neighborhood in halves, and it created a lot of concern amongst people about what this was doing to the environment people were living in. About the same time, a book called Silent Spring by Rachel Carson was published, which was looking at the indiscriminate use of pesticides and its damage on insects, and hence the Silent Spring title. This came to mind last year when I stood outside in the spring and my garden was in full flower and it was deadly silent. No insects. So we're still dealing with pesticides and the environment on that. There was the 1969 Santa Barbara oil spill. That got a lot of press. And at the same time, 1968, this photo taken of the Earth from the moon, it sort of raised awareness. Well, not sort of, it really did bring awareness of the finite resource the Earth is and how that needs to be managed and looked after better. So in 1972, the Clean Water Act was created. This was a complete rewrite of the Federal Water Pollution Control Act of 1948. It amended and reorganized the Federal Water Pollution Control Act. It created the Section 401, the water quality certification for a project that covered federal projects like power stations, transmission lines, mining, that sort of thing. And Section 402, which we all deal with today, which is the National Pollution Discharge Elimination Scheme. That is what every city has now, the MS4 permits. So that was created through the Clean Water Act. And it did emphasize technology-based controls. Sorry, this slide is out of place. Okay. So when we look at the US, in fact, Canada, I work in Canada and around the world, basically, we look at things. There's no national standard in the US for pollution control, and the similar thing in Canada, there's no real national standard. We find that different areas are looking at different types of pollutants. And we also look at this wonderful image here of the watersheds. That watersheds don't recognize any boundary. So they collect pollutants from every area they come from. So there's a great deal of difficulty when you're a company like ours trying to deal with pollutants when there's no real national standard to deal with, and you have to go state by state, region by region, literally county by county and city by city, and address individual regulations and approvals to try and help out with this whole pollution control system thing that we're trying to do. And when we look at this no national standard, for instance, up in the northwest here, we have a different type of considerations. We're looking at filtration, infiltration. As we move down the west coast, we find in Lower California, there's a lot of use of screens and infiltration systems. As we move across the country, we find separators, filters, different systems required for different types of pollutants right across the US. And this means that we kind of have to have a lot of different solutions. So I'm going to look at a few of these solutions and how they might be, how they work basically, how you might apply them, and to give you some basic understanding of their limitations and their applications. I'm going to look at separators, screens, filters, and valves. Of course, this all relates back to the pollutant. You've got to match the pollutant. So let's look at total suspended solids, rainfall, and runoff. When we're dealing with total suspended solids, we're talking about a subset of material called total solids, or the total solids in stormwater. Now, those total solids can be split into two categories, or are split into two categories. If I take my sample of stormwater taken from whatever source I go and sample it from, and I run it through a 0.45 micron filter paper, something a bit like coffee filter or something like that, what passes through that to the right is known as filterable solids. So that's everything below the 0.45 micron. That includes dissolved and very, very fine particulates, bacteria, viruses, that sort of thing. What's retained on that filter paper is called suspended solids. So we have total suspended solids. And when we look at that, we have two versions of that. We have the settleable solids. Now that's the stuff that's heavy enough to settle out. And non-settleable solids, that's the stuff that's neutrally buoyant. It has maybe a density close to that of water, and so it won't settle out. It tends to just float in suspension. And then on the other sides with our filterable solids, you get the colloidal and the dissolved. Dissolved solids are particularly difficult to remove. Because they are basically in solution, they will pass through many types of BMPs we have, including going into infiltration. They'll pass through groundwater as well. So, dissolved solids are very difficult to deal with once it's in stormwater. If we look at this in some sort of scale of size, we look at about 4.75 millimeters here. Gross solids, coarse sands, gravels, trash, debris, that's at this end of the scale. The other end of the scale, we have dissolved solids, salts, and not everything in between, going from coarse to very fine to non-settleable stuff. So we've got gravels, fine sands, silts, through to clays, through to salts and dissolved material. That kind of represents the range of what we're looking at. And when it comes to producing a device to treat that, obviously at the bigger end of the scale, screens, sumps, settling devices can generally do okay on that. As we move down through the finer particle sizes, separators, get the ponds, then we go to wetlands, infiltration and filtration systems, and beyond that we may need chemical systems as well to help remove some of these materials. And of course, the pollutants go from one end to the other. They're easy at one end, they get harder at the other, and of course the dollars associated with treatment change dramatically as you go down from one end to the other. To treat 1 CFS of water, say 28, 30 litres per second, at this end might cost, say, $10,000. At this end, to treat that 1 CFS or 30 litres a second might cost you $30,000. So that's the scale. you know, it's a 3 times factor scale there in manufactured systems. One of the problems we kind of encounter with this industry is because there's no national standard, no one's really defined in a uniform way what exactly TSS is. It's some mixture of particle sizes. So when you put your sediment sample through a series of sieves, you get a certain amount of coarse stuff retained on one sieve and then increasingly finer material retained on these finer and finer sieves. And you can plot that onto a particle size distribution graph, or as we have here, and you get a percentage of material finer than the sieve size. So when we look at, say, this blue line here, this is a material called OK110. It has a medium particle size of somewhere around 110, 115 microns. Then it ranges from roughly 125 to 200 microns down to around about 75 microns in that sort of range. Fairly small distribution, fairly coarse distribution. This is a common test sand that's been used in the industry for many, many years. Compare that to, say, this red line here. This is the New Jersey and the Canadian ETV, the Environmental Technology Verification Agency, particle size distribution that we test with, and you notice it's a lot broader range. It goes from coarser gravels right through to very fine clays, almost colloidal material down here in the 1 to 2 micron range. So when you test with this, you've got to have a lot better equipment, because this fine material in this lower range, when you're talking coarse sands and silts, is a lot harder to remove than it is with this coarser material. This green line here, Cyclocil 106, is another testing sand we use. You can see it's a slightly different, it's slightly finer at the top, but a similar sort of fineness at the bottom. So as an industry, we have lots of these different definitions of total suspended solids and what we test with. Now, we can't test with them all, and I have a database of literally dozens of different particle size distributions that have been asked of us to remove, and it's really hard to address every one. You do testing with a certain kind, and you've got to somehow translate that into performance for another one or another distribution. It becomes one of the harder parts of our industry, that no one has sort of settled on a standard particle size distribution. So let's talk about rain, runoff, and design flow and treatment flow. This is another area we get questions on. You know, what is the design flow, or what is a peak flow? So the design flow, sometimes called the treatment flow or the water quality flow, typically that is the runoff from a rainfall event associated with around about 80 to 90% of the annual rainfall, or another way of saying it, the annual rainfall is less than that flow rate. In some regulations, we see it often expressed as a water quality capture volume, but for our devices that we're dealing with here, they don't capture a volume, they're a flow-through system, so we have to convert that to a flow rate or a water quality flow rate. And in many regulations, stormwater manuals, that may also be expressed as a storm intensity. For instance, in Colorado, that's expressed as a 0.6 inch hour intensity storm. So you have to design your treatment equipment to perform at that level of intensity, rainfall intensity. Some areas it's rainfall depth, and it's not uncommon to have, say, the first ½ inch of rainfall to 2.5 inches of rainfall be considered the event that generates the water quality flow. Sometimes it's a runoff depth, and fairly commonly we see between 1 to 2 inches, between ½ to 1 inch of runoff depth. So the actual amount of water that runs off the site as being the water quality event that we need to design for. And sometimes it's an event like a 2-year storm or a 6-month storm, 24-hour duration that we design for. So no standardization there either. Just to visualize this a little bit, this is from Minneapolis, St. Paul Airport. This is from the Minnesota Pollution Control Agency's website. When you look at their rainfall over a 1 year or 10-year record, or whatever might be used to generate this sort of graph, You have the rainfall depth on the left here going up the side, and the percentage of storms that are less than that. So if we look at this right down 10% here, you're probably looking at, you know, about 0.2 inches. 10% of the storms are less than that. These sort of storms generally are so small they probably don't generate any runoff. They either evaporate or infiltrate or get lost in the cracks and crevices of the ground. So 0.5-inch rainfall depth here generates about 60% of the total rainfall in the Midwest there. And the 90% mark here, 90% of rainfall is generally less than about 1.1 inches. So that 1.1 inches is roughly what they determine as their water quality rainfall depth. And you can have something like a 1 year to 24-hour storm, and that'll be, you know, account for more than 90%, close to 100% of the storms. So you can design your equipment cost effectively wise to look at how much water you want to treat. And most regulations try and treat around about 90% of the annual runoff. Now, how does this relate to pollutants? Well, we have what we call the first flush phenomenon characteristic. This was developed through Caltrans, I believe in the early 2000s. And they looked at storms and they started measuring the runoff and measuring that runoff and how dirty it was in relationship to the time of the storm and where the peak of the storm fell. And we find that if we look at this graph here, you know, you get a lot of really dirty water in the early part of the storm. And then you get what appears to be, now on first sight you think this water at the top is cleaner. It may be visually cleaner, but it may also account for a large amount of the total load, because when you consider the volume here, there's a lot more water in this area than there is in this area. So you might have a small amount of water, but a high amount of pollutants, making it look very dirty. The amount of pollutant load may be similar up here, but because you've got a lot more water, it can look cleaner. But you have to look at your what they call the event mean concentration, or how consistent the concentration is through there. But the takeaway is that you need to treat to a certain level to capture all this pollutant, all this pollution that's coming with the water. And then on the back side of the storm, the water's been washing the site off and it's getting increasingly cleaner. So it's not practical to treat the whole storm event, but it is practical to try and treat this first part of the storm, and that's what we try and aim to do. So we try and treat the first flush. Then we have the peak conveyance, and how we handle that's important. The peak conveyance is what do we design our storm sewer to handle? In many lineal projects like DOT projects, highway projects, you don't always design for a 100-year storm. Sometimes you might design for a 10 or a 20-year storm for your pipes. It's what is practical for that site. So we have to design our equipment to handle and actually retain material when it's exposed to these peak events. So let's look at separators. You know, stormwater, as you see in this image, is kind of, it doesn't care what's on the surface. It'll wash anything off. So your separators are kind of trying to do a little bit of everything. And the regulation around the use of separators varies greatly from area to area. On the East Coast, the New Jersey Department of Environmental Protection has a lot of acceptance of their approval process, and they approve separators for 50% TSS reduction using the New Jersey particle size distribution. Now that's a fairly fine distribution. It does have a lot of material that's very fine. We'll look at that in a few slides. On the East Coast, the Washington Department of Ecology has a designation for these called General Use Level Designation for Pre-Treatment. And that generally forms around 80% removal of 110 microns and 50% removal of 50 microns. Now, this is a generalization of where these regulations are at. If you're more familiar with them, you might say, well, that's not quite right, but this is the general sort of ballpark figure that they're around. If we look in Virginia, the Virginia BMP Clearinghouse, they give about 20% removal total phosphorus. So they're looking at the phosphorus removal as well. And City of Indianapolis has a really extensive table. They have their own approval process. They look at test data and they approve equipment for 80% removal of OK110, which again is around that 110 micron. And you will find differences between each of these. The same device might have a slightly different approved flow rate for these different areas, depending on how the local engineers look at it and approve it. So when we look at separators, and I'm going to use our equipment because I'm familiar with it, just to demonstrate, there are two basic configurations in the separator world. We have the configuration which has no internal bypass. This is similar to our downstream Defender, and there are a number of different pieces of equipment on the market that are configured this way, where all the water that passes through the unit goes through treatment, and there's no bypass within the system. Everything has to go through the same flow path. So hydraulically, these pieces of equipment have to be designed to handle both the treatment flow and the peak flow and not wash out and do a lot of stuff. Then we have the configuration which has an internal bypass. And these devices have a system in them that allows the peak flow to pass, excuse me, no, I'm having a little trouble here with the screen again, to pass over the bypass weir. So peak flows come in, or flows come in, treatment flow is directed generally into a treatment chamber area, and then as the flows increase, there will be an internal weir that allows a bypass directly to outlet. So that's the two basic configurations of these separators. Now, they're all flow-through devices. They have no water quality capture volume. So as a flow-through device, you have to design a flow rate for them. So you have this treatment flow rate. You have to work out how to handle the peak flow as well and configure your site accordingly. When we look at this, there are two ways of handling this peak flow. Now we have what we call the online or inline system. This is where everything comes down. You have a single structure. The unit sits online with or without an internal bypass. If there's no internal bypass, this unit has to be sized to treat the peak, or to handle the peak flow hydraulically and also handle the pipe sizes. If there's an internal bypass, the peak flow may be easier to handle in the system. And we have the offline arrangement. With the offline arrangement, we use a separate structure and a bypass weir to handle the peak flow and the pipe sizes. And we just divert the water quality flow through to the treatment unit. I'll deal with more about those two configurations in a few minutes. So what do we know about the performance of these devices? Well, we've learned a lot over the years. When I first started about 12 years ago, I found there were all sorts of claims being made about the performance of these devices and how well they worked. We've done a lot more testing since then. And one thing at Hydro, what we've done is we've tested this equipment using individual particle sizes. So we can look at the performance by particle size. Commonly, testing is done, you throw a bucket load of stuff in the top end and you measure what comes out the bottom end, and you just get an overall reduction. If you start measuring individual particle sizes, you can see how it performs on those different sizes of particles, and which gives you much more insight into where these things are applicable and what they should be used for. So what we find is, and now this is the New Jersey distribution, which starts at about 1,000 microns, or a little over 1,000, and goes down to about 2 microns. So it covers a really broad range of particle sizes. And what we found for our testing, and this is for our design flow rate for the test unit. In this case, we tested a 4-foot unit up at around about 1.5 CFS. And at those conditions, we find that, removal of 100 microns is pretty easy. You remove pretty much all of it. Down to 500 microns, we're removing all of it. Down to 250 microns, we didn't get any in the effluent. down even to 150 microns. Now, this is around about a medium sand, coarse to medium sand, even a little bit finer than that. It was still, we were finding none of that material in the effluent. So what was coming in was being captured and retained. Getting down around 100 microns, we start to see now some of that material getting through. 75 microns, now we're dealing with the coarse silt type material, very fine sands. And then suddenly around about 50 microns, when you start dealing with the medium coarse silts into the fine silt range, suddenly the equipment goes, that's it. Whatever I'm designed to do, I've done it. And once we get down into the below 50 microns, we find that your performance, the influent and the effluent is almost identical. This is about the limit of it. So you think, okay, if I tested the whole particle size distribution, worked out my performance, I'm getting roughly 46% of that distribution. You think, oh, that doesn't sound so good. But you know, when you look at your performance down to 50 microns, which is what this equipment is really good at, it's getting 94% reduction. So if you have a site that is substantially being treated for, say, winter grit, or that you know it's getting a lot of coarser material, this equipment is going to do really, really well. And it's going to be a cost-effective way of treating that. If you've got a site where you've got a large amount, particularly commercial sites, industrial sites, where you've got a lot of heavy truck movement, and those wheels are grinding material up into very fine dust, into powder that just blows in the wind, then you're going to be looking at something better than this, because that material is going to be very fine and very difficult to remove. So it's very much a horses for courses, know the site situation. Okay, so let's go back and just cover off the internally bypass, externally bypass thing and move on to our next equipment. So when we have internally bypassed devices, what the device is trying to do is manage the water quality flow, the peak flow, the pipe size, and manage that all in one structure. So you've got this real juggling act going on, and that you're trying to manage head loss as well. So generally these devices with an internal bypass will treat less water, but they'll pass a greater flow. And so you have this compromise. So they're really good devices for retrofits, because they're like manholes. They generally plug and play. You can just put them in. They're easy. Contractors like them. They generally come fully installed. You just drop them in the ground like a normal manhole. Generally, what will control sizing will be either the peak water flow, or the pipe size, or the number of pipes, or the peak flow. The treatment flow is something that you sort of select the size based on what you want to treat, but often we'll find on sites there'll be some other system that'll control, or some other condition that'll control how big this unit needs to be. For instance, if you've got large pipes, you're on flat grades, it might be the pipe size that dictates how big this unit needs to be. If you're on a steep site and you've got high flows, or you've got you know, high amount of runoff, the peak flow might be the consideration. Now, there is one thing you need to really consider when you're looking at internally bypassed systems, and this really applies to any system with an internal bypass, and that's the effect of backwater. When you have a wear, the amount of water you can push through treatment depends on the head difference between the water on the upstream side and the water level on the downstream side. So it's that differential pressure that allows you to push water through your treatment system and out. When you have tailwater, that differential pressure can be greatly reduced by that tailwater. So if you have a flat site that may be subject to tailwater, and this is particularly true to places like Florida, where grades are flat, groundwater's high, you could select off the charts or from the vendor's information a device that, say, is supposed to treat 4-foot manhole, treat 0.7 CFS, because that's what can be pushed through under normal conditions, and you backwater it, this loss of head pressure may push the device into bypass much sooner than that. It may go into bypass at 0.1 CFS, so you're not getting the treatment level you need, And to correct for that, you need to be able to lift that wear up to create the differential pressure again. That's difficult to do with internally bypassed units because these things are generally pre-made, pre-constructed devices. They don't come with adjustable wears. So that brings us to these externally bypassed units and where they become very useful. Initially, you might think, well, it's two structures, it's more expensive. That may not be so. When you're sizing a system based on either peak flow or large pipe sizes, upsizing the unit for that particular condition may cost more than, say, pushing it offline and putting a bypass structure in and using a smaller unit offline. So when you have an offline unit, you can now design this bypass structure. And that bypass structure can have a wear in it set to account for any backwater conditions. And really all you're trying to do is push the water quality flow through to the treatment unit, which is now sized only for the water quality flow. So when you're dealing with, say, 8, 10, 12-foot structures online, if you can go to a 6 or an 8-foot structure offline, often that's a lot less cost than going offline than staying online, because you have to consider craneage, weight of transportation, that sort of stuff, cost of ownership and cleaning. So the other advantage of going offline is that you can place this unit where you need to place it so it can be maintained. If it's online, it's forced to be where the pipe is, and if that pipe is in the middle of the road, that's a problem. It could be in the middle of a parking lot. If you go offline, you can place it where it can more easily be maintained. Now, we've done a series of webinars over the last couple of years in maintenance. It's been one of those. More detail on design has been one of those. We're putting together a web page that puts all those webinars into one place so you can go back and look at them. So which is better, internally bypassed or externally bypassed? Really, there's no real answer to that. Each is suitable for a different condition. Externally bypassed units generally do much better for trash and oil, and so they can be downsized to treat only the water quality storm, and they don't, so you minimize the size of the treatment unit. And a smaller unit is often easier and more cost effective to maintain. Online units can often be larger, but they do suit sites. Contractors like them because they feel like they're doing things better by just digging one hole or a smaller hole. They generally can handle multiple pipes more easily, and surface inlets often more easily as well. Yeah, so I've kind of covered a little bit of this, online or offline, which is better. Again, it's a horses for courses thing. If the peak flow, the pipe size allows you to go online and you're not going with enormous manhole sizes, then onlines will generally be a cheaper option. But when you're dealing with large pipes, large peak flows, tailwater conditions, the offline arrangement is going to probably be a better arrangement to work with. If you're dealing in an area which is unregulated and you're dealing with equipment that you don't know a lot about, or there's very little test data for, we would always recommend placing the unit offline and limiting the flow to it and externally bypassing it. Even if it has an internal bypass, putting it offline and limiting the flow that goes through that is a much better way of handling the peak flow, because you never know, if there's a lack of test data, what the washout factor is in that when a peak flow goes through it. There are regulators that require all units to be placed offline. It doesn't matter how much testing you've done, they want them offline purely to stop washout, and that's a good, safe option. Units should not be placed online ever if there is no washout data. If you have no data on what the washout is and how they perform with peak flows, they should never be placed online. They should always be placed offline. Sizing these units, I'm just going to touch on this lightly. We've done whole presentations on sizing, but I just wanted to bring up the topic here. There's two ways of sizing these units. One is a single water quality event. That's where you take a single storm and size for that storm. And this is typical for any water quality unit, really, whether it be a separator or a filter. whatever it might be. You can size using, say, a rational method or TR55, and you size for a single flow rate, and you select the equipment based on removing 80% TSS or 20% phosphorus at that flow rate, and that dictates the size. There's another way of doing the calculation, which is called the net annual or historic rainfall method, and that runs a long-term historic rainfall record through the device and calculates what we call an annualized removal. So it takes into account all the smaller storms and a few of the bigger storms, and you get an annualized removal. That requires a spreadsheet or a piece of software to run that calculation. Generally speaking, the single event sizing method will make a larger unit. The annualized event will make a slightly smaller unit because it's influenced by the rainfall that is small. You know, there's a lot of rainfall that are small events, and so there's an influence of the proportion of small storms in there, whereas this just draws a line in the sand and says, treat this storm. I don't care about the smaller storms or the larger storms. And when specifying this equipment, you really want to look at three things. You need to specify a treatment flow rate. If you're not designing the equipment or you're asking the vendors to size the equipment, we need to know a few things. The design flow rate, we need to know the peak flow rate, and we need to know a particle size distribution. Now this, just saying 80% TSS is a real shot in the dark, because one vendor could size on very coarse material, one vendor could size on very fine material, and the two pieces of equipment will be quite different in size. So defining a particle size distribution and referring to maybe a standard like New Jersey, City of Indianapolis, Washington DOE is a good way of getting around that. And if you want more information on that sort of thing, we have other webinars on that, or just contact us to talk about that. But not defining particle size distribution is one thing that we find is one of the greatest headaches for an engineer, for a vendor. We'll be calling you saying, so what particle size? And you'll think, well, you know, I really don't want to think too much about this. This is going to take some time. And there are a number of stormwater manuals and regulations where they simply say 80% TSS with no definition of TSS, which more modern, more recently updated stormwater manuals are addressing. It's becoming more common knowledge now that talking about TSS is an important part of sizing these pieces of equipment. So now I'm going to just breeze through a few of our other devices and just talk about why, what they are and what they should be used for. I don't want to be on talking to you all afternoon. So let's look at these screens. Now, screens are interesting things. They're gross pollutant removal devices. They can handle large flows, but they also can remove a lot of organic materials. So in places like Florida, we find we can use screens for removing phosphorus. And in California, screens are used because there is a fairly strict regulation around trash, because, well, they have a lot of beaches and you don't want trash on beaches. So in Florida, we find screens used for phosphorus and debris, and in California for trash. We don't find screens used a lot around the US or in Canada, but they are really useful devices. When you consider the amount of plastics and polystyrene and that sort of material from the food industry in our native, in natural waterways, you would think that a screen would be a standard piece of equipment on every outfall. In my opinion, it should be. The photo on the right I took in Kentucky on the Cane Creek bike path. Just looked over the side of the bridge. I'm in the middle of the fields. There are horse farms all around me, and that's what I see. Just a lot of floating visual debris. And that pollution is just easy to remove before it gets in your waterways, but once it's in the waterways, it's really hard to remove. So trash screens generally are larger structures. They can take big pipes. They're basically just, you know, big sieves on the system. Here's a picture of one of ours being manufactured here in Wisconsin, where I live. You see the screens. They have weirs at the back. These are just not complicated devices, but they are really quite useful devices. In terms of design, ideally the screen should have a maximum, you want to maximize the volume of these things. The debris they're catching is quite large volume material, so volume is an important thing of the capacity of these. Sediment capture on these devices is not great, but flow rates is. So you can look at treating to a basic level. Now you might be pre-treating to a pond or to a discharge point, and you can treat 29, 30 CFS, 162 CFS. We can build these things significantly large to handle these flows. We also have, there are a number of products on the market now, like this manhole-based systems of screens. They do really well at capturing a lot of trash off smaller areas. You've got to really consider the capacity, how much you can store in here and how often to clean them. If you're screening from areas which get a lot of material, you may be cleaning these things monthly. Filters. Filters are, again, devices for cleaning basically stormwater, for TSS, for dissolved pollutants like dissolved phosphorus, dissolved metals can be removed with them. They capture a much larger range of pollutants. Regulation in the US around this and in Canada, basically we find a lot of following of the New Jersey DEP regulation. Now New Jersey tests for 80% removal of TSS. It's a lab protocol and it's only concerned with removal of sediments. The Washington Department of Ecology, they have multiple levels of approval for filters. You can get general use level designation basic, which is 80% TSS based on field testing. You can have general use level designation enhanced for a filter as well, or even just for a media that removes metals, copper and zinc type of material. And you can have a separate approval for phosphorus removal. To get phosphorus, you've also got to actually have basic as well. So there are multiple levels of approval for filters. Those are the two main ones in the US that I know of. I don't think there's any other references. Many stormwater manuals throughout the US, Canada, in fact, Australia, New Zealand, many places refer to those two approval processes around the world. So they're looked at all over the world. When it comes to filters, we have, again, really two types. We have media filters. Media filters are just that. They contain some sort of proprietary media in them, which may be carbon, peat, zeolite, sand. It's a mixed material designed basically remove a range of particles from sands through to metals, phosphorus, dissolved materials. They have multiple processes going on for absorption and adsorption, filtration. So they're a good general purpose Swiss Army knife type filter. Then we have a different type of filter, and this is called the ribbon filter or the membrane filter. These filters are just that. They're membranes. You might think of them as pool filters, as like your Brita water filter. They are a physical strainer in the system, and these primarily target particulate material. They don't have any process for absorption or absorption. They are physical strains in the system. They do really well for particulate material. Now, the reason you have these two systems basically is a little bit about test protocols and passing for approval. But when you look at a media filters generally work pretty well down to about 20 microns. They'll start letting material through somewhere around 20 microns. You'll start getting pinholing and escaping material. Whereas a membrane filter can be sized with a membrane pore size less than 20 microns. Now, where this comes in is, for instance, like in New Jersey, this is the New Jersey particle size distribution here. To get 80% removal, basically you've got to remove 20 microns and above. Everything has to come out, which means you kind of need a membrane filter in there, because if you have a media filter and it lets some of this through, you'll never get 80% removal. You might get 75, you might get 65 or whatever, but you won't get approval. So membrane filters got developed basically to pass this protocol, but they actually have a lot of use when it comes to very fine particulate removal. Key elements of filter design. Now, filters, ideally, if you're talking media filters, the media should always be stored when the unit isn't working above the static water level. So there should always be a drain down system to lift media out of the water, because you don't want media, which often contains some organic material, sitting in static water and being affected by the water chemistry, or whether there's hypoxic or anoxic conditions in the sump. So media filters generally like to be aired between events. Ribbon filters, however, being just strainers in the system, they can sit in a submerged condition. So we'll find generally that ribbon filters will have lesser head loss requirement. They'll work at lower pressures, but they'll have other considerations. Again, we have to consider the design flow, the treatment flow, but we also have to consider filter capacity, because it's easy to size a filter for 80% TSS, but it'll only last one storm because it'll be exhausted. So you have to size a filter for longevity or use. And we try and size filters for around about a year of use before you have to carry out maintenance. So that's one consideration that we really have to look at closely with filters. So now let's look at bioinfiltration and infiltration systems. Now these are commonly used, called tree in the boxes, some of them. We see a lot of these around. A lot of people like these. They consider them maybe to be LID. Regulation around these systems varies greatly. In California, I was looking at some of their regulations last week. If it's a tree in the box and it's a physical concrete box, they don't consider it LID. They consider it a manufactured system, and it doesn't qualify as low impact design. In many areas, you put a tree in a box with a media, and they do call it low impact design because it does, to some degree, mitigate runoff. Now, that's one of the advantages of this type of system. These systems help slow down the water, so they try and match the runoff values of the site to mimic that of the pre-development site. So these will slow the water down, they'll treat the water, they'll have a volume component, an evapotranspiration component as well. So infiltration versus filtration. Most of these systems, if it has an underdrain, many regulations will consider them to be purely filters. They're not infiltration systems. So if you put an underdrain under one of these, it's a filter system. If you have no underdrain, it will be considered infiltration. A lot of these systems are designed to have a tree in them. We've developed a system here called a bioinfiltrator, where the system is merely an enabling framework where you can use whatever media you need, and the tree is unconstrained to enable it to grow. We see a lot of systems, tree in the box systems, where the root ball is constrained, and that can lead to problems with growth and tree die-off. So you really want to look at systems that allow the tree that you're using, or the material that you're using, to thrive and survive. That is a major consideration to look at when using systems like this. Realistically, these all contain either a proprietary or a non-proprietary soil mix. And you've just got to give whatever you're growing in it the best chance to survive. The system we produce, the bioinfiltrator, it's made of stainless steel. It's a modular system. It doesn't need craneage. So we've really looked at the system and said, how do we make this easy to use? Because a lot of small contractors don't have the ability to lift and put heavy structures in. Most of these systems throughout the industry are modular. You can just build them up like a Lego block. And the advantage of systems like this is that you can go to sites like the Washington DOE or your local stormwater manual or the BMP, International BMP Clearinghouse, and you can find recipes for soils to put in these that have been well tested and approved for the pollutant you want. And you can use these soils with these systems without having to go to a proprietary system. Some of the key things, the soil blends, you really want them to be free draining, loose, unconfined, and most of them are designed around sort of that 50 to 100 inches per hour infiltration rate. That will be limited by the underlying native soil. That will control how much you can get into the ground. So And TSS removal, these things, because of the way they are, do pretty well at generally treating everything. Of course, again, your limiting factor is your underlying soil. If you have underlying heavy clays, or if you have very high groundwater, you're going to have trouble with these types of systems. On the other side of these systems, they require a higher ongoing maintenance, regular maintenance. You've got to have a system that you can pull apart. You want to be able to rake out the trash, the leaves. Then you want to rake that top few inches of soil, maybe replace it every couple of years. You've got to keep that top, things will blind off and really go impervious very quickly in that top few inches if you don't look after it. Okay, I have another product here. I know I've really hit my 1 hour limit here. I'm just going to touch on this very quickly. This is rate and flow control, basically, with vortex valves. This is a product that is a full subject on itself, like all of my guests, but this one generally generates a lot of interest when I do presentations. There are no pre-approvals on a product like this, but the regulations exist around rate control. And most regulations I encounter are either a minimum outlet to stop blockage from your storage system, from your pond or your underground detention system, or you're looking at trying to match pre-development flows to your post-development site. And there's lots of reasons why you're doing that. Now, just a quick video here on how these vortex valves work. Hopefully this will run on your system. The water comes in, and there's no moving parts, but what it does, it spins the water. So as the water comes in, it spins and it creates a core of air. This is just like water flowing down through a plug hole. And you get that tornado effect. And it's that core of air that goes down in through the system that creates the throttle back. So you end up with a larger opening overall, but it's choked back by the air that's the air core that's created in the valve. And that process creates kind of an odd-looking head discharge curve. When we compare that to an orifice you might design, and it might be, say, this one here. Let's just say that's a 1-inch orifice, and as the head on the orifice increases, the flow increases, you get to your design point. The corresponding hydro break will be about twice as large, and it'll have this larger opening, so you get more flow at low head, and then the air core develops. It actually reduces the flow with increasing head, and then it starts to behave with a stable core, and you get to the same design point. The key factor is here, the area between these two graphs is water that you can pass downstream without storing. Not only that, you have a larger outlet, so you're not blocking, you're not going to block as easily, and you actually get a faster cycle time on the tank, so you can reduce the downstream high flow time. So, you know, outlets, larger outlets, they can make smaller storage volumes. They can allow you to have deeper footprint tanks, deeper tanks with smaller footprints, and better hydrograph matching. And that's sort of vortex valves in a nutshell. Quick word on approval processes. This is one of our biggest problems. I've mentioned before, we spend a lot of time on approvals. New Jersey has a system which runs through the New Jersey Corporation for Advanced Technology. Certification, Washington DOE certification. City of Indianapolis has a good, Canadian ETV is now using ISO 14034 for certifying new technologies. Any technology that is uncertified should always be looked at closely. It doesn't mean it's not good technology. It may mean that the vendor that's invented it can't afford to get through this process or is in the process of doing it, but certified processes, these certification processes are really useful for looking at the systems and actually ensuring that they work and do what they say claim to do. Quick word on treatment trains. A treatment train is a multiple stage system. It involves either a stage 1 pre-treatment followed by a storage infiltration type system or a secondary treatment, maybe followed by a flow control, and then followed by a filtration or final infiltration stage for water polishing. That's sort of a treatment train in a nutshell. Many regulations or stormwater manuals have a process for developing treatment trains. Now, this is the understanding of a treatment train can be a little fuzzy at times. This example comes directly from the Wisconsin DNR here, who saw this exact type system being developed and presented as a treatment train for approval. And the engineer had developed a small pond, passed from there into a larger pond, into a third, even larger pond, and it calculated an overall removal efficiency, but had missed the point that all 3 ponds were the same thing and that you really only needed the last one. But in a treatment train, pond 1 could actually be a 4-bay. So you could effectively move it in there, create a 4-bay for maintenance, and then go through to pond 3. So, you know, the treatment train understanding sometimes gets a little fuzzy. We see systems that may incorporate manufactured systems or manholes in series. Now, manholes in series are not actually effective treatment trains because when you think about it, water comes in, the sediment starts to settle. Anything that passes through the first one is reset to the original height, and it can continue doing that and pass through all 3. But if you combine them and remove the common walls, it would be effective. So the same volume, same size, is more effective than the 3 smaller ones. We get this question because we do see occasionally people asking, can I put one system downstream of the next system and then go to a system downstream of that? And say, yes, you can, but you've got to consider the particle size shift as they go through each system and design the downstream system to address those finer particles that are coming out of the upstream system. Now, this is a valid system. It's not really a treatment train, but you can split between systems and halve the flow rate and therefore improve the removal. So systems in parallel do very well because you're sharing the load between 2 individual systems. So an effective treatment train generally runs through a pre-treatment system that may be screens, separators, baffle boxes, generally removes, treats maybe high flow to a low level of treatment. Then you go into a larger system where you might have rate control and treatment for finer TSS, and then into your final system with maybe a flow control system. This might be a wetland, an infiltration system, a gallery, a filtration system that can't handle the big flows, but you know, you have a flow control device and you can do your final treatment at that point, and that's an effective treatment train. Many of these, how to calculate the overall removal is in some BMP manuals. I'm not going to go into that because I'm kind of out of time and I don't want to keep you all day. So I want to say thank you very much for listening in. If you have any questions, please email me. Please fill in the exit survey for us. That will be most helpful. And if you have any questions, feel free to email me. In about an hour, you'll get a follow-up email with my contact details as well. So thank you very much and have a good afternoon.